So today I'm going to tell you a little bit about a real-time analytics framework we built at Yahoo. What does real-time... Okay. All right. So I'm going to tell you about a real-time analytics framework we built at Yahoo. What do we really mean by real-time? In our context, real-time is an event that occurred less than a minute ago and being able to see it in an analytics dashboard. For example, if I were to go to the Yahoo homepage, the fact that I went to the homepage and viewed the page should be visible in an analytics dashboard. In practice, it's usually much lower than a minute. It's on the order of like a few seconds. My name is Hiral Patel, and I'm going to introduce myself real quick here. I'm a senior principal architect at Yahoo, where I worked on real-time media analytics, reporting for search and native ads platform. I've also worked on big data at various companies using both open source as well as enterprise solutions. So a lot of the things that we see with real-time now in open source have probably been around in like the enterprise for more than a decade. So today I'm going to go through some of our use cases, our goals for building a framework, a few example architectures, and some of the tools and technology we ended up using. Our use cases generally revolved around publishers and editors. As a publisher, I want to see how my content is performing in real time. I want to see what's driving views. How is the content doing in terms of recirculation? Are people going on one news article and going to another one, or are they going off-site? How's the engagement on videos, for example? And essentially, they want to capitalize on high-performing content. Editors, on the other hand, want to be able to promote content that is currently trending or content which may become viral over a period of time. So there is a data science component to this as well. So why build a framework, right? So Yahoo's publishing products group, which is the group I worked for, has many web properties. Each has its own product management and development teams. This means developer efficiency becomes very important. We want to decouple the teams so they can all work towards their analytics goals for real-time analytics, yet provide for a common framework. This means that we can reuse all the optimizations, the monitoring, the application metrics across all of those use cases. At Yahoo, we have many different technologies that are used for analytics and serving content. Our technology choices are generally grounded in what we can reuse and what we may be able to bring in. So in general, we tend to reuse the same technology we already have instead of trying to bring in new open source projects unless we have a committer on hand or someone willing to take responsibility for maintaining that open source tool. Let's take a look at a simplified view of an example architecture where we're producing minute aggregates. So traditionally, people would, when they want to see real-time analytics, they would just aggregate per minute or per 15 minutes, per 30 minutes, whatever they could get done in a batch fashion and load that into a database. And that kind of pervaded into the real-time space as well because we don't have any data store in general that can actually handle the amount of events and updates that need to happen in real time. So what we have is a Lambda-style architecture, which is where Nathan Mars talked about having the speed side and the batch side. We would do something similar. We'd have events coming in as a stream of events into a storm topology, where we generate in-memory aggregates and push them into a database. On the batch side, we would have log files which are copied to Hadoop. We run MapReduce jobs, produce the hourly aggregates, and load them into a database. an alternative to this is an architecture where we have a data store which is capable of doing real-time aggregations of raw events. We just produce the processed events and push them directly to the real-time store. Now, there are a few examples of this, notably Druid, Pinot, or Kudu. In order to make it easy to onboard new use cases, we built supporting tools. For consistency, we needed a way to centralize schema management on both the real-time and batch sides. We reused an internal CI/CD framework for Storm, which allows us to easily onboard new topologies through configuration to multiple data centers and environments. On the batch side, we wanted to make sure that the data was being loaded consistently, so we built a data loader which was resilient to failures. We also needed to perform data lookups on Yahoo-specific metadata, things like site, property, and et cetera. So all the downstream use cases would have this data available instead of having to do the same kinds of lookups on their own. For the data lookups, we built a fault-tolerant service which served the data sets to our Storm topologies. The topologies periodically would check to see if a new version of the data set is available, and if so, they would grab it and refresh it. And the same was true for the service itself. It would basically go to Hadoop and see if a new version of the data set is available, and download it and serve that. The data sets on the Storm side were locally backed by LevelDB, so most of our data sets were less than 2 gigabytes, 3 gigabytes at most. And so serving those out through a REST service was pretty easy to do. And all the updates on the Storm side were done asynchronously in a separate thread, so it didn't really halt the real-time processing in any way. So now that we have the supporting tools, we needed to make it easy to build topologies. So we built common libraries on top of a configuration-based topology builder. This allowed us to build generic classes for data ingestion, processing, and loading, and reuse them across all of our use cases. This also allowed us to centralize common serializers and deserializers, compression codecs, and all the different lookups that were used for the dataset service. Another important requirement which drove how we built this framework was performance. We needed to process a certain rate of ingestion from our internal fire hose, which we call data highway, and also the processed events which were to be produced by all the different use cases. This meant we had to do capacity planning around I/O, network I/O, disk I/O, and CPU utilization. Let's go through an example. Let's say we have a fire hose producing events at a rate of 6 gigabits per second. We would need to pre-process all of our events and perform our common lookups and push those events to Kafka. If our replication factor was 3 and we had a 15-node broker, that amounts to roughly 153 megabytes per second disk I/O on each broker. If we had 10 topologies reading our pre-processed events from Kafka, our network I/O across the 15 brokers would be approximately 78 gigabits per second, which is a lot of I/O, right? So what can we really do about achieving this level of disk and network I/O across the Kafka cluster? One of the things we started with was to start benchmarking, of course. We needed to identify the performance characteristics based on various configurations of replication, message size, and compression codecs. So we took a POC cluster and ran these benchmarks. Here's an example benchmark we did. And as you can see, the higher throughput was achieved as we increased the message size and obviously at lower replication factors. We used all the benchmarking tools that Kafka comes with as a part of doing this benchmark. Well, what about the I/O in Storm, right? So there's network I/O in Storm. As data is transferred between Storm workers, it is serialized on the source host and deserialized on the target host. We used, in order to reduce the network I/O, by default Storm uses Java serialization, which is bulky. So we ended up using custom Creo serializers with configurable compression codecs to reduce the size of the data that was sent across the wire. We experimented with various compression codecs and ended up using LZ4HC based on our results. And of course, we want to filter out unwanted events as early as possible. In order to increase our throughput on Kafka, based on the benchmarks you saw, we needed to increase our message size. Since we wanted to guarantee at least one semantics, we used Kafka's synchronous writes. So microbatching was needed to achieve the required throughput. We made the batch size configurable so we could easily experiment and make adjustments. We also added 2 levels of compression. Each batch itself was compressed. Each batch consisted of a list of events, and those events themselves were compressed. And we also had, for each of those events, we also had a meta event or a subset of event data. So the meta basically contains maybe 10% of the actual event's data, which could be used to quickly filter if we're interested in this event or not. Right? So this saves us all the cost of deserializing the event, decompressing and deserializing the event. This in itself, when you're like searching for a needle in a haystack, speeds up your real-time processing quite a bit. So microbatching roughly added 100 millisecond additional latency, given a batch size of 10% of the event rate. So if our event rate was 1,000, we would say our batch size would be 100, right? And at that, we would add an additional 100 milliseconds, which is nothing really. We also gain an additional 10 to 15% of compression due to the batching, even with the 2 levels of compression. Let's look at an example batching bolt that we have. It's a subset of the actual class. I just took some important aspects of it. It's an example batching bolt we would use in Storm. It's responsible for processing the incoming tuples and passing valid batches to the underlying batch processor. And the underlying batch processor is responsible for managing the lifecycle of the batch. It invokes all the registered event processors for each event and accumulates the batch of events and flushes when either the size or time limits are reached. It also provides a mechanism to access the compressed event through lazy decompression and deserialization of the actual event. So we won't deserialize and decompress it unless we actually need to access that event. The event processor is pretty straightforward. It's just responsible for its business logic. So most of the developers using the framework just wrote a class that extended the event processor, and everything else was configuration. So the event processor is responsible for processing each event and producing one or more events. It's possible that you may have one event that has maybe all the section data for a given page view, and you're doing analytics at the section level. So you'd have one event which would then has maybe 10 sections. So you would end up producing 10 output events for one input event. So you're doing a 10x increase in volume there. So all the output events were also part of the batching framework, so which essentially allowed us to scale the processing of events even if we had an explosion of 10x. The event processor also can maintain state within the batch life cycle through the initialize and finalize methods. So initially, if you didn't have a real-time store and you wanted to push 1-minute aggregates, you would just implement the initialize and the finalize methods, and you do your in-memory aggregates in the process record method. So I've shared with you our journey of building a real-time analytics framework. It wouldn't have been possible without all the engineers on our team and other teams who contributed to it. And I hope this talk has sparked some new ideas which will help you in addressing some of your real-time use cases. Questions?
Is this framework used by all Yahoo, or is it other companies part of the product?
So it was built as a part of the publishing products group, which is responsible for most of the web properties. Mail is separate, search is separate, but it's also used by our search and native ads platform. So it's used both on the audience side as well as the ad side.
Thank you, guys. Thank you, Hiral.
Thank you.